So, hello, good morning, everyone, and really nice to see you here. And thank you for inviting me to this event. And I'm really pleased to be here. And this place actually, it's probably the most favorite place for me as well. I spent a lot of time in this place when I was a student. I was a biology student, so we were catching butterflies and other creatures, and yeah, so a lot of sentiments. And okay, coming to the presentation, and I already been presented as working for the agency, but I'm also working for as a PhD student for the university. And so my presentation would be combining some things from my work in agency and my work as a researcher. And maybe during this presentation, something would be not clear because it's so clear for me, and for you might be, how to say, you might have questions, so please raise your hand and I will try to answer if there is some things not so well explained. So my presentation is about what are major environmental problems with rivers connected and how do the climate change would affect them. But this is mainly based on our research, on our, how to say, modeling efforts which we've done. And so the major environmental problems connected to rivers, they are a lot, and certainly I cannot put all of them in this hour, or hopefully less than an hour. And there are, how to say, big problems with different impairments of rivers, like damming, hydromorphological alteration, also microbiological pollution, stormwater, hazardous substances, invasive species, flooding, droughts, etc. But in this presentation, I want to focus mainly on three ones, which is close to my also field, is eutrophication, diffuse pollution from agriculture, and climate change. And these topics is actually, how to say, affecting all the waters in Lithuania. It's not maybe dams are affecting particular water body, stormwater or buildup of imperial serious water bodies close to the cities. But these three are affecting all the water bodies which we have, and they are affecting in how to say, in certain trends. So this pie charts show more or less what are sources of pollution for the two nutrients which we have, nitrogen and phosphorus. And these two nutrients are the main drivers of eutrophication. I did not include transboundary pollution here. It's also, how to say, in sources is accounted as another source, but it's also combined of agricultural background and point source. So without putting transboundary pollution, we get this kind of distribution. So the most nitrogen loads coming from agriculture in Lithuania is 72%. Phosphorus is 54%. And the next big source is actually natural, is background pollution. And the next big source is a point source pollution, which for nitrogen is only 3% of cumulative load. For phosphorus is more, it's 13%. And then we look into the point source loads in Lithuania. What has happened is actually updating and, how to say, building up the waste water treatment plants. We saw what the loads from the point sources has decreased substantially. much more for phosphorus than for nitrogen, but still the effect of point sources, how to say, has been reduced quite a lot. And so if we look from 2002, it's dropped 3 times for phosphorus and less for nitrogen. But if we look from 90 or 95, it dropped much more even. So the big problem, the big issue for us is agricultural pollution. And agricultural pollution is not distributed, how to say, equally in all territory. We had some territories in the middle of Lithuania and the southwest part, maybe north part, where we have actually the most agricultural activities concentrated there because of the suitable soils and low slopes and other conditions. And these where we have the most problem with water quality. And the problems are related mostly to nitrogen. And so this territory is like around a third of Lithuania where we have these problems. And if we look to the water bodies, we have around 1,200 water bodies. And we evaluated around 400 something of them might be in this or are in the risk category because of agricultural pollution. And how does the land use look like in Lithuania? Why we have this agricultural pollution problem so acute? And this place where you are is actually not, you will not see much agriculture. This is the most used for mushroom picking and berries, and this is the most famous area for this. So it's not so obvious here what is the problem, but the 60% of all Lithuania is actually agricultural territory. And 30% are forests, so you are in this forest here. And well, the rest are small percentages, but out of the 60% land use, half of it is used for intensive grain production. It's like winter wheat, summer wheat, barley, etc. And these areas are used quite extensively, like being fertilized, tilled, etc. And this is where we see also the most leakage of nitrogen is happening. And what happened since, how to say, since 1990, we saw what after, how to say, collapse of Soviet system, all the farms was not so well organized, not so well run. And so we saw a drop of, as well, of loads from agriculture, but also of certain intensive areas. But since 2003, 2004, then we joined the EU, the intensivity in agriculture increased, and so that did increase the growing of crops, especially with grain crops. This probably is the most productive way, how to say, of getting, providing the most income for farmers as well. And it increased quite substantially. So this followed also increase in mineral fertilizer. When we see here is organic fertilizer, it's actually depends on how much animals we have in Lithuania. And it did not change a lot, but when we compare on the same scale what happened with mineral fertilizer, it's here I think we show the numbers for the sales in the country. So since 94, 95, we saw increase in 300%. Since 2003, compared to the last figure, we saw increase of 51%. But still, I mean, this could not mean very good things for for environment and especially for rivers. So this basically, if we look at this graph, we see change, how much it's changed since 2000. And this yellow is how much fertilization changed. It's not absolute, it's changed numbers. And so we see also greenhouse gases from agriculture increased because of this change with use of mineral fertilizer. We also see what load to the Baltic Sea increased. Here we see, how to say, ups and downs because it depends from the weather conditions and hydrometeorological conditions, what will happen with fertilizer. But it's still on this what is happening. I mean, following the application of mineral fertilizer. And so this is calculated also loads for the HELCOM. And this is only shown on these figures, our loads, how to say, removing all this in transboundary and also normalizing them for the weather conditions. So we have, how to say, requirements for two places, for Gulf of Riga and Baltic proper. And so these two figures are for nitrogen, and we see what, okay, it's jumping up and down, but we also are seeing this trend is increasing, and the red line is showing what is the maximum we are, how to say, allowed to pollute the Baltic Sea, what is put in Baltic Sea action plan. So we are on the wrong way, at least for this moment. Then it comes to phosphorus, and phosphorus mainly, like historically, it came mainly from point sources. Now it's like more agriculture maybe, or balanced. It dropped significantly with update of wastewater treatment plants, and so for at least for one basin we are in the right place, and but for the other not so much, but still, I mean, it's not changing in the wrong direction at least. So, and you maybe know what Baltic Sea has a lot of problems with eutrophication, and 97% of Baltic Sea suffers from eutrophication, and Coronian lagoon is actually one of the most eutrophicated places what we can find. And but this thing what is happening in agriculture does not really impact Baltic Sea. It doesn't impact also our coastal waters, and we see what the water quality in this picture is not good in any place in our coastal waters. And also, if we look this graph, which is, I think from here, it's also showing what it's been decreasing in for nitrogen, at least parameter, in following years. So it also what we saw. Then we looked in all Lithuania, it's also we saw more places actually not meeting nitrate criteria. And let's say this is 2007, this is 2017, we see more red dots. Of course, we had more monitoring stations, but we also had more problems in places where it didn't have problems before. And also, if we look to the monitoring of rivers which are clean, not so clean, and so on, we also saw these trends, at least in the last years. And what does it mean also for our management? It also means what the cycle, the new river basin management plans, it also saw, then we evaluate, we see potentially what we will have much more risk water bodies because of the agriculture. And now with the climate change, I think you all maybe heard this news of IPPC IPCC report, which is was released 2 days ago. And yeah, this is happening, and this is could be seen as well. So here you see the color bands, which is showing how is temperature, world temperature deviating from the average, and so we see what is from colder getting really hot, and and we can see the effect of climate change on everywhere around us, and so the question is, what does it mean? How we will see the changes in our environment, and this is why me with my colleagues, we try to evaluate this as well. So I think I lost a few slides, but okay. So basically what it is, this is one article which actually trying to look what does it mean for Europe, and it means actually different things for different part of Europe, because in our, let's say, zone, which is here, it means more precipitation, more flows, at least from the models what have been presented. In the south, it means, of course, less precipitation, less drought. So this is like a pattern, but the places which already too much humidity will get more humidity, with too little will get less humidity, and we see this is northern part, so it depending on scenarios, it's like 1.5, it's like, I think, like Paris Agreement. 2 is 2 degrees warming, 3 is 3 degrees warming, and in northern we will see a substantial increase depending on the climate change intensity. And in other places in Europe, we will see mainly decrease of precipitation and decrease of flows. And what we can see also, this is what for northern region, this is 3K is 3 degrees warming. We see what here is low flows, this annual total precipitation. We will see what we will be in more precipitation and more flows for low flows, and of course for high flows. And so it depends which scenario will take place. But this is not the only thing what is happening. I mean, another thing what is happening, we will get more extremes, and this one is from Helcom research. It shows that in summer the percentage of this how to say low flows will be also decreased. So it means that summers could see less flows. Not could, but probably will see. So, but let's say also high flows will be increased, and so we will see, how to say, much more extreme events, either dry or very wet, and in general, I mean, here would get more wetter, but the extremes will be in either way. And here, this graph just shows, I mean, it is for Sweden, but it's for similar latitude as ours. So it's just showing what all these models show, what precipitation for all them should be in the plus, I mean, change. So what we did with my colleagues, we selected a few scenarios, and so we all know this Paris Climate Agreement says 1.5 degrees, no more. Now it's 1.2 already, and we so we selected 2 for our analysis, RPC 4.5 and 8.5. It basically means warming of between 2.5 and 3 degrees, and and also warming of 5 degrees. And I'm not sure how much you connected to this climate jargon, but I hope you will understand. If not, please ask me. So why we didn't select this 1.5 is just because this is the recent graph. Maybe what is happening now, how realistic is the Paris climate agreement as well? Because in our opinion is not so much realistic, because so this is our emissions already, and this is what happened because of COVID. But now what we hear is also how to say emissions bounce back, and we see what in order to reach this 1.5 degrees, this is what the maximum we can emit is also this cumulative area under. So it basically means now already by 2040 we need to be at 0 for the world, and this is how to say looks quite unrealistic, at least because we already starting very late. So if we will start even later to do something about our emissions, it will get even closer, maybe to 2035. Then we need to be carbon neutral for the planet. So yes, so how to say, let's say this is our scenarios which we used and evaluated what it would mean for our rivers. So just this was a tool we used, SWAT model, which was set up for all Lithuania and included part of Belarus and and little parts of Poland as well. And we used 7 regional climate model data and also one model for this 100 years. And I hope you will be able to see these figures, or at least I will try to do my best to explain it. So we run for Lithuania, and this is our results. Maybe our authors had different, but so I will try to say what we got. So precipitation is also these 2 scenarios. If we have, let's say, mild scenario, not so a huge increase, but if we have this extreme scenario, we will see quite a huge increase of precipitation. And also what it would mean also what this is basically because of temperature, because days we will have much less snow and ice cover, and also much less of ice and snow warming. So and this means that we will have so much less surface runoff, but more water will be infiltrating into the ground, so we will get more water coming from the groundwaters, from the tile drains, from the lateral flow, and also we will get more water coming, how to say, already being in the river. And if we look to the monthly, and this may be a figure which is really hard to see here, but the thing is, what the biggest change we will have is actually in the spring months, which used to have some melting of snow and so. So the melting of snow, maybe if we take the extreme scenario, it would be not existing anymore, because all water would be, how to say, not snow. And also we can see what how to say, in winter we will get more also tile drain and lateral flow, which would be because water would be infiltrating, not staying on the ground. And so the flow increase also would be the most pronounced in winter months, and for the spring, because the water will be already infiltrated and flowed, it will be decrease, because how to say, and and recharge also to soil water, because in spring we have a lot of water melting. It fills soil water content. So during the plant growing season, soil water content would be also decreasing, because it will receive, it would have fed much less water. So okay, maybe it's a little complicated, this thing, but the idea is what water distribution would be different, and it will affect in certain ways and in some negative ways agriculture. It will affect in negative ways, let's say, flows, and distribution will be different. But not sure if I managed to explain well, but maybe other things will get you some ideas what is happening. At least when we look in the spatial maps, how the changes and where will happen. If we look in the absolute amount, we see the changes will be happening in, let's say, in these areas in west and east the most. Because these areas already receiving the most of precipitation. So addition would be to these areas the biggest, but if we look to the percentage, the middle would be receiving, how to say, the bigger increase. And since this area is connected to agriculture, so the more water in this place also means how to say, maybe better conditions for agriculture, but also maybe better conditions for washing out or leaking the nutrients. Because so then we look in the changes in loads also. What does it mean? This is yearly loads. Okay, maybe I didn't put the right explanation. Here are two periods. And also, this is important, historical is 2000 to 2020, mid-century is 2004 to 2060, and end century 2080 to 100. So, and these are two scenarios. This is mild, this is extreme. And so we see because of the decreased surface runoff, we will see less sediment yield, and also everything that is connected to sediment, organic phosphorus or organic nitrogen, it would be decreasing. But everything what is mobile in the soil, like nitrates, we see a huge increase in tile drains, in lateral flow, in groundwater flow, because more water infiltrating into the soil, more mobile nutrients would be leaving the soil. Yeah, and I'm not sure if I should try to explain monthly changes, but let's say monthly changes would follow probably the water flows as well. So the more water flows we have flowing through the soil, more nutrients we will have how to say lost from the soil as well. Okay, and what we already observed in our monitoring data, we also observed what we have for the colder period, which is in green light, we see more increased concentrations. Here are aggregate of some monitoring stations and the average for 4 years. And so we see this is 1960, 2017, what we already see, but there is some trend in winter much, how to say, stronger. And this is also because in winter, if we don't have snow, there is nothing to protect the ground. So the bigger rain and the ground is, let's say, open to being flushed, and this is happening. So these two things, what I already explained, the increase in fertilization and also climate change, we see how they combine, and our loads are also increasing into water bodies, into the Baltic Sea. Yeah, and this is what it is for the spatial changes, what it means. Also, because I did these graphs and it's so easy for me, but probably I didn't explain what it means. So these are end century, these are mid-century, and they are comparing what changes will happen comparing to the historical period. So we will see here nitrogen load, it would increase in all areas, but and this is absolute change. But in the middle, it would increase the most. It's actually the middle is where the agriculture is concentrated. So depending on scenario, but how to say, these places with more agriculture, they are much more susceptible to the leakage of the nutrients. But if we look to the absolute change, we can see what is also following absolute, sorry, not absolute, the percentage change. It's following the precipitation as well, because the more precipitation it receives also in some areas, let's say west and east, it will have high effect to the losses of nitrogen. And if we look to the sums of the water flows, sums of the loads, what will happen? So here we see water flows for the two scenarios, and so we see what for this intermediate scenario, let's say, it's not increasing so much, but for the extreme scenario or the worst case scenario, it will increase a lot, and most of water will be coming from lateral flow and tile drain flow and groundwater flow. This is where the increase will happen. So if we look in the nitrogen loads, this also would see increase in both scenarios, but much more higher in extreme climate warming scenario. For phosphorus, it's not so clear. It could be either way. Here we receive, but it's decreasing a little, but it's not really so much sure. So here you can see the percentages, how much each scenario would change. But then we look into water concentration of nitrogen. It did not really change much because we have more water maybe, but some water bodies, which here you can see the purple or the brown ones are where water bodies are at risk because of the not meeting nitrogen criteria, and blue are not at risk. So some green ones, which comes here, they become at risk because of the climate change. And there's also light blue, which become not at risk because of more precipitation, maybe more dilution. So it does not change some so much substantially, but there are some water bodies which become at risk just because of the climate change. Another thing what is also important, which we did not study, but I want to mention, is also what this is important, how to say, we expect to get more loads because of the climate change, or loads be affected in this, how to say, to be increased by climate change. But also one thing is not mentioned, what the eutrophicated water bodies, they do release also greenhouse gases, and this is like a kind of circle, and especially, how to say, lakes and lagoons and like a Baltic Sea, with warming climate, it's going to release especially methane and other greenhouse gases, which is also contributing to the more warming. And another, how to say, direction is also because temperature, we will have a longer period of growing, and also, so this allows in the water bodies which have a lot of nutrients, it allows longer time for the algae blooms and how to say longer time for fixating nutrients, and also so increasing eutrophication even more. So this is like a kind of feedback mechanism which, if we get eutrophicated water bodies, they do provide, how to say, more greenhouse gases, and also they already by themselves eutrophiate more. And temperature is a big factor for this. So we try to look what it actually means for reaching water framework directive. Of course, have worse conditions because more loads to reduce. Also, we will have how to say, the things which would trend in negative direction, temperatures like bigger growth periods and so on. So we look to the 5 measures like less fertilization, more grasslands, no tillage, winter crops, and stubble fields in winter. And this is the maximal amounts which we were able to put in Lithuanian model. So this basically shows what baseline scenario, which already I showed, what we will have increased nitrogen. For phosphorus, not so clear, but fertilization, less fertilization, which was minus 10% less than now. We saw what effectiveness of this measure of it would increase because in future we will have more leaching prone conditions, more rain, more precipitation. So if we put less nutrients at the source, we will have less nutrients at the end. So this will be more effective measure. If we look at no tillage measure, so it will be less because it only stops the water and nutrients which is coming from the surface. So if we have no surface runoff, we have not so much reduced pollution. For grasslands, it's more or less the same. Just at the very extreme end, grasslands would be much more efficient because, how to say, comparing to this, the leakage would be much more higher at this scenario. And if we look for winter crops, we will have not so effective. We can see the effectiveness lost because winter crops, the ones which we grow now, is not suitable for future conditions with extreme climate, because future conditions, and this is what we put in the model, these crops will die. What to say, because they are used to grow in this cold climate, and so you cannot put them maybe just for a very short period. So we also try to look if effectiveness would be different in different parts of the Lithuania and how it would be changing, let's say, with a period, with a climate change scenario. So this is an area where we have already a lot of problems from agriculture, and each measure, how to say, here we see the effectiveness of each measure put in different part of Lithuania, and we see what actually even we have the problems here, but now the measures are the most effective in the west part and the east part, because actually the places where we get the most rainfall. But with the climate change, at least for fertilization, we will see the much more effectiveness in the middle, because this place will have higher leakage of nitrogen, and we can see, if I could explain this graph, I will try. The red line is here for effectiveness of measures, cumulative effectiveness of measures in this agricultural result, and blue in other part of Lithuania. And so we see this red line is actually let's say if we take each of these measures, we see it's traveling past this blue hill. So we see the effectiveness maybe at the beginning is the same in the agricultural risk areas and not agricultural risk areas, but then we will have much more effectiveness in agricultural risk areas. And this means basically what in future the measures would be so much more important or so much more effective in this area where we have agricultural activities. Yeah, for phosphorus, phosphorus is not so sensitive, but for phosphorus is also we have, for exception of only fertilization reduction measure, but for phosphorus also we have the same kind of the places with more precipitation is more effective for application of measures. Okay, and I'm very close to them, maybe, so we will have a question. And so the last slide, or the one before last, I actually looked at the, we looked at what does it mean for the yields, for the crop yields as well, the climate change. So we see substantial drop in the crop yields. And yeah, this is basically affected by, how to say, different of these extremes, and also we try to look at what does it mean for the crop yields if we use different measure, and do we change it or not. So yeah, for it does affect the crop yields in different ways, and the main idea is also from this what more extreme climate will be, how to say, affecting more. And this was my last, this is my last slide, and thank you for attention. And I hope it was not so much complicated graphs and etc. But if you want to ask me, or I don't know, what was not clear maybe, or how can I explain something more, I will try to do my best. And this is a nice picture which I found, because we deal with wastewater water framework directive. It just set the stage for the next presentation for your Gita. Okay, thank you for your attention. So if you have any questions, please.